Hi, my name is Huang Yanzhang. I'm going to introduce my research interests. Basically, my research interests include two parts. One is from Cauchy-Riemann geometry, the other is from integral geometry. I study the intersection part between those two fields and try to understand the geometry in Cauchy-Riemann manifolds while integral geometry approach. Recently, I'm also cooperating with some faculties in engineering departments to solve some problems from image processing by integral geometry formulas. In particular, I focus on the study of Heisenberg groups, Hn, which is a special case for Cauchy-Riemann manifolds. There are two main questions in my research. The first one is the equivalence problem. We ask, when are two geometric objects in the Heisenberg groups set? This is a joint work with Qiu Honglin, National Tsinghua University, and Lai Xinhua, National Qinyi Da, between 2016 to 2018. We proved the fundamental theory of curves and surfaces in the Heisenberg groups. We studied the groups of region motions in the Heisenberg groups and the Mori-Cardan forms, and also we defined the curvatures for curves and the surfaces. And the theory states that given the curvature function, we can prescribe a geometric object such that its curvature is the given one. The other question is that we ask how close are the Heisenberg groups and the Euclidean spaces in the geometric sense. As we have already known that the Euclidean spaces are a special case of Riemannian manifolds, and there are two perspectives for the Riemannian manifolds. One is to regard it as some manifolds in Rn, the other is the abstract manifolds. As long as we have the Euclidean space, then we can prove the fundamental theory of curves and the surfaces. And this is a beginning of integral geometry. There are many interesting topics in integral geometry. And follow the diagram, we have several similar results. At the beginning, there is a Heisenberg groups, and it is a special case of the CR manifold, and also two perspectives for the CR manifold. One is you can regard it as a real submanifold in Cn, or an abstract Riemannian manifold with complex and contact structure. And we have already done for the fundamental theory of curves and surfaces. After that, I also proved the Crofton formula in the Heisenberg groups and the containment problem, also the projected volumes, and recently I proved that the Cauchy surface area formula holds in the Heisenberg groups, Hn. Next, I'm gonna show two examples on the plane. Actually, we have already proved the similar results on the Heisenberg groups. The first one is the Crofton's formula. Given a curve on the plane, we can get the length of the curve by the formula. On the left-hand side, it is an integral over all lines on the plane, and we calculate the number of intersections of all lines with the curve C. The second example tells us that given a convex domain M on the plane, the area of M can be obtained by the integral formula. It is an integral over all lines on the plane, and we have to calculate the chord length of each individual line L intersecting M. There are some common features for those integral formulas. On the left-hand side, they both are probability quantities, namely randomly throw a line L on the plane. If we can calculate the number of intersections and sum it up, then we can get the approximation of the length for the curve. And similarly, we can have the similar explanation for the second one. And on the right hand side, both are the geometric invariants. in the following sense, they both are invariant under the rigid motion, the rotations and translations. But however, we still have a lot of challenges in Heisenberg groups due to the lack of tools to deal with the context structure and the complex structure. And many researchers around the world working on the related topics, including the United States and Italian schools, and also some researchers in Spain and France. So any comments and suggestions are all welcome. And if you are interested in these topics, welcome to contact with me. Thank you.